Welcome, everybody. Thank you, Joan Peracaula, for accepting to talk on the CosmoVerse seminars here today. Joan obtained his PhD from the Autonomous University of Barcelona in 1985 in one-loop renormalization of the electrode parameters in n=1 supersymmetry. He is currently full professor and head of the particle physics and gravitation group in the Department of Quantum Physics and Astronomy at the University of Barcelona. Joan is an expert on physics beyond the standard model, supersymmetry, and QFT and cosmological backgrounds. Today, he will talk to us about running vacuum in the universe, theoretical frameworks and implications on the cosmological problems and tensions. Joan, you can start when you are ready. Thank you again.
Okay, thank you very much for the introduction and for the invitation. My talk today will be, as you can see, on the running vacuum framework and the implications on cosmological problems and tensions. So this means that these are the guidelines of the talk. So there will be some introduction to the vacuum energy and the cosmological constant problem, even from some historical perspective. Then we will move to some more technical issues related to dynamical dark energy and the running vacuum in quantum field theory. Not and beyond, here it says beyond, but I will not have time to go beyond this, although there is things that can be said beyond quantum field theory. And then, if there is time, I will try to show that this framework has non-trivial implications on these cosmological tensions, as we know nowadays, and the conclusions. Okay, so as we know, there is these Einstein equations, which were introduced by Einstein in 1915. Okay, they were introduced without this lambda term here. And then 2 years later, he introduced the lambda term because it is compatible with the general covariance. And the reason basically was because he wanted to make the universe static. So by introducing a positive lambda, he showed that this was possible, although this equilibrium is actually non-stable. Okay, but at that time it did the job. Okay. And the simplest version of this lambda term, which is well known, is that it is a constant, okay? And the standard argument goes like follows. So one defines this Einstein tensor here, which is on the left-hand side of the equations. Then you take the covariant derivative, which is automatically 0 because of the Bianchi identities of the Riemann tensor. And then using the fact that the covariant derivative of g mu nu is 0, and that usually one assumes that the energy momentum tensor of matter is also locally conserved, and usually one assumes also that this constant, Newton's constant, is also constant indeed. So you take it out from this equation. So the only thing that you are left is that with the fact that this derivative of lambda must be 0, the normal derivative, and therefore you conclude that lambda is constant. But as you see, there are a lot of assumptions in between, okay, about the strict conservation of the matter energy momentum tensor, that G is constant, and that there is nothing else to take into account. In any case, if lambda is constant or not, you can define this quantity, which is a ratio between lambda and Newton's constant, together with some factor, and this has dimension of energy density. And since this energy density has nothing to do with matter, which is put on the right-hand side of Einstein equations, then you speak of vacuum energy, or in general on dark energy. So this was actually the article, the paper where Einstein introduced this term, okay, This was on February 8th of 1917, so 107 years, okay, and 13 days. And you see it was a paper on cosmological considerations on the general theory of relativity. But then in 1931, 14 years later, in this other paper on the cosmological problems of general relativity, this constant was put down. I mean, it was removed from Einstein equations. In fact, just 1 year later of removing the term, he wrote a paper with De Sitter, okay? In this paper, you see on the relation between the expansion and the mean density of the universe. It is amazing to see that, for example, this sentence here downstairs, it says historically, it was just 14 years later, before. Historically, the term containing the cosmological constant lambda was introduced into the field equations in order to enable us to account theoretically for the existence of a finite mean density in a static universe. It now appears that in the dynamical case, this n can be reached without the introduction of lambda, okay? So it was just killed. It was then 2 years later was resuscitated, so to speak, by Lemaitre, okay, this paper. And it was actually in this paper where Lemaitre related this lambda with vacuum energy. At that time, he did not make the association with quantum field theory or even quantum theory, but introduced this quantity as something that would measure the vacuum energy, whatever it be, okay? So he has been this term several times on, several times off, depending on the necessities of astrophysicists. But still, you see, we are at 2024, 107 years later, and still we are trying to understand what is this term, what is the physical meaning, and we are even ready to abandon it and replace it by other ersatz entities that we call dark energy. Okay. In any case, the first connection of the lambda term with quantum field theory or quantum theory in general, it was performed by Zeldovich 50 years later then Einstein introduced the term, okay? And he related lambda and the corresponding vacuum energy density with the vacuum energy in quantum field theory. And his first thought was that it would, I mean, this kind of diagrams in which we have a fluctuation of matter fields, okay, they would induce a quantum contribution to the vacuum energy, which would be proportional to the quartic power of the mass just by dimensional reasons. At that time, he used the proton mass. Nowadays, we would not use a proton mass because it is a composite object, but still, this is what he did. So it is 1 GeV, essentially. So rho lambda would be 1 GeV to the fourth. So, of course, this is much bigger than the critical density at present, which is of order 10 to the minus 47 GeV to the fourth, okay? So the discrepancy is very large, and he could not understand, and in fact, we still don't understand why this situation occurs. This is what we have measured, and this is what we have computed. There is a mismatch, which is completely unacceptable. In a second thought, playing with dimensional analysis, he used the 6th power of the proton mass times the gravitational constant, which is given by the inverse of the Planck mass square. And then you get 10 to the minus 38, much smaller than 1, but still 9 orders of magnitude bigger than the critical density. So this doesn't solve anything apart from the fact that there is no particular reason for this combination apart from dimensional analysis, okay? So So we reach the situation at present, okay? This is the situation in which we have the so-called O cosmological constant problem. And this problem is basically the fact that what we measure, the vacuum energy density that we measure, this physical value of rho lambda, is not just the vacuum term that we have, for example, in the Einstein-Hilbert action, okay, this term here, or if you want in terms of lambda here, is not just this. You have to add something else, which is the induced contribution to lambda, to the cosmological term. And this contribution is something which is connected, for example, as you can see here, is connected in part with quantum field theory, and also in part is connected with the ground state value of the potential of the fields. Okay, so if we have, for example, some scalar field, say Higgs field, then there is a ground state value, if you want a vacuum expectation value from the point of view of quantum field theory, which provides a contribution if there is spontaneous symmetry breaking. And moreover, there is this generic 0-point energy contribution from any quantum field, okay? And these two terms provide a very significant contribution to the induced vacuum energy that you have to insert here. And then you have to make sure that the sum of these two terms give the measured value, 10 to the minus 47 GeV to the 4th. As we know, these two terms are usually very large, so you have to play a very significant fine-tuning here, which is part of the cosmological constant problem. So you see, this is, in a picturesque way, the vacuum fluctuations of any quantum field, okay? So here I use an electron and a positron, but you can do the same. I mean, you can draw these diagrams for any particle, muons, quarks, whatever, okay? And then you have to sum over all these modes. Here we have this H bar, which denotes the quantum effect, right? And here we have the frequency associated to the modes, and you have to sum over all of them. Of course, this sum is converted into an integral, which is badly divergent. And this is the reason why then you are in trouble. So as you can see, the conclusion of this is that the quantum quantum vacuum is not vacuum at all. It is full. Is full of fluctuations, and these fluctuations play an important role, which causes us a lot of headaches in connection to the cosmological constant problem. As I said before, there is also the contribution from any scalar field which is subject to spontaneous symmetry breaking, right? So here you have the Higgs potential, for example. Then this parameter here, which is not the mass of the particle, is just a parameter. Under these conditions, you get this vacuum expectation value, right? And this expectation value, then you insert it in the potential, and you get the ground state value of the potential, which is dependent on the Higgs mass, the physical Higgs mass, or at least it can be put in this way, times this vacuum expectation value, right? So for a long time, for example, the Higgs mass was not known, so this could just be some theoretical business, but nowadays we know that the Higgs mass has been measured 12 years ago with a mass of about 125 GeV. So you put here this number, then you take the expectation value of the Higgs field, which is connected with the Fermi constant, which is well known, right? And then you get something like 240 3 GeV, and then you get this contribution, which is of order 10 to the 8 GeV to the 4th, which you have to compare with 10 to the minus 47. which is the value of the critical density in the same unit. So you see that the mismatch is tremendous. So in general, you see that the vacuum energy, which is a combination of vacuum bubbles and spontaneous symmetry breaking, that is a combination of things, is something that in principle gives a lot of problems, and these problems are expressed numerically, for example, by considering the different contributions from, say, QCD, from chiral and gluon condensates, from the electroic standard model, okay? So all these contributions, which are well known and perfectly under control, because this is the standard model of particle physics, they are all between 40 to 55, 56 orders of magnitude larger, okay? And of course, if you take the ground-unified theory contribution of quantum gravity, you get this famous number, 123, which I would not care to match at this point, because it is enough to see that with the standard model, we already have a big problem, right? So this problem is connected with the value of the measured value of the cosmological term, which is in a strong disagreement with the predicted value. In any case, the mass value or the energy value associated with the measured cosmological density is the quartic root of this number, this 10 to the minus 47. So it is a pretty reasonable scale, between 2 to 3 millielectron volts, okay? But we do not understand what kind of physics we have behind to this in principle reasonable number, okay? So the fact that we have a problem here is not surprising, that then people, of course, wants to go beyond lambda. And this beyond lambda is what we call dark energy, which usually is dynamical in most models, okay? And so the idea is that we try to replace this problem, the cosmological constant problem, by other problems, okay? So we put them other names, dark energy. Somehow we forget everything about what I have said on in connection to quantum field theory, and then we substitute the cosmological vacuum energy density with these new entities, which can be of many kinds. Okay, so generically, these various forms of dark energy do the following. So you put here in the vertical axis the densities. Here you have the scale factor. Okay, so we have the evolution of radiation. Okay, we have the evolution of matter. There is a crossing here, and then matter dominates. And then what we do is to introduce some field or something similar, which we call quintessence, which is totally subdominating in the early universe, but then it decays very slowly as compared to matter and radiation. And then at some point, okay, so it emerges at the dark energy epoch, and we are here at present with the dominance of this term, okay? We can also do the same with other objects that we call phantom dark energy, okay? Which rather than slowly decaying, they slowly increase, okay? And then again, at the same point, they surface and then dominate the universe. The difference is that in terms of phantom, then the universe in principle undergoes a big rip in the future, okay? So this is the kind of thing that we do to replace the old problems, but of course we introduce new problems. However, my point of view that I would like to summarize in this talk is that I would like to come back to the whole idea of vacuum energy, because from my perspective, one can reformulate it in a way which is not troublesome as compared to what the traditional thinking supports of this situation. But let us first be naive. What it means to be naive. Let us consider the zero-point energy in quantum field theory in flat spacetime, okay? So let us consider this bubble diagram for any particle. Let's take, for example, scalar field. And then the zero-point energy, of course, is a series of in powers of the Planck constant, h squared, h cubed, which count the number of loops. So let us stop for the moment at this one loop case. And in this way, we just try to evaluate that sum of modes that I have shown in that picture with the bubbles, remember? Okay, this is the same term. Now we write the frequency in terms of this wave number, and then we replace the sum with an integral, okay? We integrate over angles, and then we are left with this integral here on the modulus of k. And of course, if you count the divergences here, you get 2 plus 1 plus 1, so it is quartically divergent. So that's the reason why we have to put a cutoff here. So this lambda, please do not confuse with the cosmological constant. That's why I have put UB. This is just a cutoff, okay? So then we perform the integral, and of course the integral is proportional to the quartic power of the cutoff. And then if you consider the second term with this, then you get the quadratic contribution, and then finally you get the logarithmic contribution, okay? But in any case, it is badly divergent. But you can renormalize it. And of course, when you normalize it, then you are left with this log term here. And then you replace the cutoff by some regulator mu, some scale. Actually, this is some normalization scale. And okay, so the cutoff has disappeared from this expression, and then you get the renormalized expression of the vacuum energy at one loop. And as you see, it is perfectly finite. What it means is that you have just introduced some counter terms that have canceled those divergences, and then you are left with this perfectly finite quantity. And then you could say, okay, I'm happy because now I got a finite quantity, so the job is done, and now I can be happy. In fact, it is not so, because you see that this contribution here is proportional to the quartic power of the mass. It is not proportional to the quartic power of a cutoff. But it is proportional to a quartic power of a mass. And any mass in the standard model, even the electron, provides a contribution here, which is much larger than the critical density, which gives the scale of the cosmological constant, right? It's the same order. So unless you put here a neutrino of 1 milli-electron volt of this order, remember that the scale the mass scale associated to the cosmological constant was a few milli-electron volts. So if you put here a neutrino of a few milli-electron volts, then yeah, no problem. This would provide a sensible value. The problem is that you cannot just contain yourself with the neutrino. You have to sum over all particles. So once you put here the electron, muon, even the top quark or the W mass or whatever, of course, then you get contributions which you cannot afford. So again, we have a problem, despite the fact that we got a perfectly normalized result. Okay. So and moreover, if you think this kind of deduction here, if you try to make sense of it, you will see it makes no sense at all. And the reason is because, I mean, there is no contact of these formulas with gravity. Where is gravity here? There is no gravitation. This is flat space, remember, okay? So even if you then replace this scale here with some physical quantity, whatever, related with cosmology, I mean, this calculation wouldn't make any physical sense, just because gravity was completely ignored. So this is just a formal calculation, a mathematical calculation, which does not lead to any physics. So what is the next step? Of course, the next step is to introduce gravity. And one first thing that you could try is to, for example, consider weak fields. So it means perturbations around the flat space-time. And then this ubiquitous square root factor, you could expand it in terms of this h mu nu, or if you want the trace of it, okay? So you could start introducing gravity effects, which in principle are just classical gravity effects, because these are classical lines of the external gravitational field, okay? And then you can interpret this expansion around flat space as a sum of diagrams, in which the first diagram, which is quartically divergent, corresponds to the cosmological term. And then there is another diagram in which you have infinitely many tails of the external gravitational field here. There is an insertion. And this diagram is quadratically divergent because now you have a propagator here. And the next diagram, you have two insertions and therefore two propagators. And now the diagram is just only logarithmically divergent. And the next diagrams will be, for example, finite. This would provide a correction to the cosmological term. This provides a correction to the gravitational constant, 1 over g, in fact. And these are contributions to the coefficients of the higher derivative terms. So at least at this point, you feel the effect of gravity because you take it into account. Okay, so this was actually the idea that we had a long time ago, which in the sense that we thought that the vacuum energy eventually should be expressible in terms of power series of the Hubble rate, which is connected with all these tails here, right? And in fact, as we will see, if there is time, this kind of approach can also have implications on alleviating the current tensions. But before doing that, so let me explain this framework in more detail, which, by the way, can be, I mean, if you are interested, there are some reviews which I have written over time here. And there is also a stringy formulation of this approach, which I wrote with Nick Mauro-Matos a few years ago. And so where you can find all details. In any case, the meaning of this power series expansion can be better appraised if we take just a couple of terms. For example, this term here and this term here, this and this. The reason why I am not considering the linear term and the cubic term is because these terms are not expected from the point of view of covariance. In principle, you can put all the terms in the expansion, and under certain conditions, phenomenological conditions, maybe you need these terms. But in general, you expect by just covariance arguments that you only get the even power. So let us just take the constant term and the first even power. If this coefficient here would be 0, then you are left with just the cosmological constant term. So we expect that the coefficient of h squared should be small. And we will call it 3 times nu. I mean, nu is just a small parameter, and this 3 is just for convenience. So this is the kind of thing that we would expect. And in fact, using this expression, you can even predict by solving the corresponding Friedman equation and Bianchi identity and the expression for rho lambda that I have mentioned before. You can predict that G, the gravitational constant, quotation marks, is actually not constant, that it evolves logarithmically with the Hubble rate with this coefficient, with the small coefficient nu, okay? So there are realizations of this framework in which you can have both a running cosmological constant. This is the language I will use, the running cosmological constant, because it is running, it is evolving with the cosmological expansion, and you can also have a running gravitational constant or coupling. Okay, so this is the kind of thing that you can get, but in principle, this is just wishful thinking, because there is no model behind all these formulas at the moment. Okay, so this is how we proceeded some time ago. So we first tried to interpret the previous formulas as being related to a renormalization group equation of the vacuum energy. Right? This renormalization group equation was an expansion in powers of this of some scale, which then we would associate with a physical quantity, and we take here again just the even powers, mu squared, mu to the fourth, and so on and so forth. And then if this scale is connected with some physical observable, as we do in for example, in the standard model of particle physics, where we associate the renormalization scale to some physical quantity, some physical scale, for example, the energy of the accelerator where the experiment is being performed. In this case, we don't have any acceleration. We have the universe, and the universe, I mean, a natural scale of energy in the universe, if it is described by the cosmological metric, the Freeman metric, also Walker metric, should be h. Okay, so mu squared would be a linear combination of h squared and h dot, which have the same dimensions. Okay, so in inserting these into the previous expression, we get this expansion here, right? So we have all these contributions, and for the moment, to make it our lives simple, let me just take the powers of 8. Let us forget for the h dots for the moment, okay? In order to get a simple expression. So the previous expression just boils down to this one here, where I have extracted a convenient prefactor, 1 over gn and some coefficients. So rho lambda would be, in this case, a function of h, but above all, there will be a constant term, and then two dynamical terms, both of even order, one as h squared and the other as h to the fourth. Of course, this term h to the fourth is completely irrelevant at present. So at present, we expect that the universe, if it is describable on these grounds, it should be it should evolve with it should have a vacuum energy, which is essentially a cosmological term, plus some deviation, which is proportional to h squared. But of course, if we move to the early universe, then we expect that this term will dominate and that it would trigger inflation. And in fact, it does. We have solved this model. And this produces an inflation, which is different from, for example, from Stravinsky, okay? And it is associated to this running vacuum idea. But even at that level, we still don't have any theory behind. Okay, so in order to construct something which is more serious and formal to substantiate that structure, recently with my former student, Christian Moreno, Pulido. In this paper, we presented, well, we have presented several papers, and in this paper, we presented the first attempt to make sense of these running vacuum model ideas in the context of quantum field theory. So we take Einstein equations, and then we take also some scalar field, just a scalar field. And in order to make our lives simple, because calculations here become complicated immediately, because remember that we are in curved space-time, we just take a kinetic term for that field, we take the mass term, and then we take a non-minimal coupling of the scalar field to gravity, to curvature. We do not consider at this point spontaneous symmetry breaking contributions, which would be provided by some effective potential. The calculation is sufficiently complicated not to introduce more things here, okay? So the first thing is that we compute the energy momentum tensor, the classical energy momentum tensor. This is well known, it's very easy for this model. And then the next point is to introduce quantum fluctuations, which means that the field is split into a background value plus a fluctuating term, okay? And then the idea is to compute the expectation value of this energy momentum tensor, because this is supposed to provide the energy momentum or tensor of vacuum. And this should be provided by the fluctuations of the fields at this delta phi bar here, okay, plus the term in the action already, which is already in the action. So the sum of these two should provide the expectation value, the vacuum value of the energy momentum tensor. For the calculation, we use this conformal metric. So we introduce a scale factor and conformal time with this signature here. And then what we do is to expand the fluctuation in Fourier series. So it means that we introduce creation and annihilation operators when we move to the quantum calculation. These are interpreted as creation and annihilation operators. And then here we have the modes, okay, for each k as a function of the conformal time. And the corresponding Klein-Gordon equation satisfied by this fluctuation in terms of these modes just becomes this simple, in quotation marks, equation. I say quotation marks because it is not just a harmonic oscillator equation. It is more complicated because this omega k here is not constant. So this is not a constant frequency. It depends on, you see, on the scale factor, which is a function of time, and it depends also on curvature. So it means that this equation, despite it is linear, is difficult to solve, and it is much better to try to solve it in another way, in another form. Basically, we introduce this change of variable, so to speak. We replace hk by wk, and then the corresponding equation satisfied by wk is a nonlinear equation now. This was linear, this is nonlinear, but this nonlinear equation is a typical WKB equation. I mean, it can be solved using the WKB approximation, provided these derivatives of WK with respect to time are small. If they are small, it means that they do not cause a large perturbation to the main term. So one can just perform a WKB expansion, which in this context is called an adiabatic expansion, adiabatic regularization. So we expand that function in terms of, I mean, in 0, order 2, order 4. This order counts the number of derivatives, actually, of the term, okay? So, for example, these 2 here, you see there are 2 derivatives here. Here you have 1 derivative square. So it means that basically there are 2 derivatives. this term here is the square of the previous expression, or sometimes, or just the previous expression times a second derivative of omega. So this is a fourth order term. There are four derivatives of the scale factor here, and so you can expand, and then what you get indeed, after you compute these derivatives explicitly and insert in the expansion, you get this expansion here. And in this expansion, you can see that the linear terms that I promised that they would not appear because of general covariance, in fact, they do not appear. And what you are left is just with even powers, h squared, h to the fourth, h to the sixth, okay? And then you have to compute, of course, the expectation value of the energy momentum tensor. And in this particular case, I will just fix mu nu equals 0, okay? So just the 0, 0 component, which is connected to the vacuum energy density. And you get this expression in terms of the modes. And remember that the modes were expanded using the adiabatic expansion, and then you get the complicated formula. I don't want to go into the details of the formula. Just I want to mention a few terms such that you can understand this formula. I mean, this formula is very easy to understand if you just put your attention on this first term, 2 times omega k. I mean, this term here is just a very well-known expression of the vacuum energy density in flat space-time, exactly the same formula that I have shown in a previous transparency. This is that integral. I didn't put the h bar here because I put it to 1, but it is the same formula, okay? But apart from this formula, which is the only thing that you have in flat space, you see all the other terms depend on h prime. By the way, this curly h is just the same h, but in conformal time, okay? So this is the Hubble function in conformal time. We used this Hubble function for the calculations in conformal time, but then at the end you can of course convert it back to the ordinary Hubble function in cosmic time, okay? But so this h is the Hubble function. So all the other terms, as you see, depend on h. So when you are in flat space, all the other terms are 0, and then you are just left with this one here. So that's why I told you that the flat space calculation is just a mathematical exercise. It has nothing to do with physics. But this one, it does, because it depends on the Hubble function, and therefore this vacuum energy density is a function of the cosmological expansion. All the terms are sensitive to this Hubble function, okay? Again, I will focus now on the red terms, only these 3 here. So here we have the these 3 terms, 1, 2, and 3, which I have just collected here in order to highlight them, because they are the only divergent terms. You see, the red ones are divergent, but the black ones, despite they are complicated, they are convergent. You can see, for example, this one here. There is omega k to the 5th power. So this goes like the 5th power of k. And here you have 3 powers of k. So obviously this one is finite. This is also finite. And all the other ones are finite except the red ones. The red ones is you have to compute it first, and then to do something in order to get rid of the divergences. You have to renormalize them, okay? So that's why I have highlighted them here. This quartically, this is a quartically, quadratically, this is quadratically, and logarithmically divergent term. This term is logarithmically divergent, okay? And so this is the result for a scalar field. If you would repeat the calculation for a fermion, you would get the similar expression, except that you would get only the quartic term, this one here, quartically divergent, and then you would get a logarithmically divergent contribution, like this one here. You see omega 3. We also have omega 3 here. but you don't have now a quadratic divergence, okay? Now, the interesting thing about this scalar contribution and the Fermion contribution is that you can see with your eyes that if this theory would be supersymmetric, for example, I'm not claiming that I'm using supersymmetry, but if this theory would be supersymmetric, then there would be an exact cancellation of quartic divergences, because you see this guy here has a plus sign and a factor of 4, and this guy here doesn't have this factor of 4 because it is a fermion. So I took a trace, the trace kills a factor of 4, but of course then when you put the same number of fermions and bosons in the same multiplet, you get the same contribution with a minus sign. So these two guys would just cancel even before the normalization. However, the other terms do not cancel, so you have to renormalize it, okay? So this was only to show the kind of divergences that we get, and that we do not expect that there is cancellation of these divergences, only in the quartic ones, in the case that the theory would be supersymmetric. In fact, is not. And here you have the contribution from this first term, which is the standard one, the quartic divergence. Okay, so as I said, we have to normalize the theory, and the prescription that we use to normalize the theory is to take the energy momentum tensor. I mean, I'm taking at this point the 0,0 component of the fluctuating part, I mean the vacuum part of the energy momentum tensor, and then I take it on my shell, m, this is the mass of the particle, and then we subtract the same quantity at another scale, m, some arbitrary scale, but we only subtract the adiabatic orders which are divergent, which are the ones which I have shown before. These are the 0, 2, and 4. Remember that only the even powers count here. So the 0, 2, and 4th orders are divergent, and we subtract these orders to the on-shell value at an arbitrary scale. You do this with this formula that I have shown you before, and despite it is quite bulky, the subtraction gives a very simple result. It's just this one here. Okay, so the result is, this is a renormalized result. Okay, so you get this term which is constant. It depends on the mass of the particle and this renormalization point. And then, most important, there are two terms which depend on the Hubble rate. So it means that this 0-point energy, in fact, is evolving with the cosmological expansion. So one term is relevant for the present time, h squared, and then there are terms which are of 4th order, 6th order. I mean, these dots here means that you go to 6th order and whatever order. But of course, then you don't need these terms at low energy, because you see they are of order 4. So here you have order 1, but you have 2 derivatives of h. Here you have 1 derivative square. So all these three terms are of the same order. So you can just forget them for the study of the present universe. Okay. And then what is the result? Okay. So then we compare. We have to insert this renormalized vacuum energy on the right-hand side of Einstein equations. These are the Einstein equations. You can recognize these equations. You see we have G mu nu here. This MPL is the Planck mass square reduced, because there is this factor of 8 pi here, but it is the Planck mass square reduced Planck mass square. Here you have the rho lambda term, okay? And one cannot forget at this point the fact that we are renormalizing the theory, and we have to include also a higher order term in Einstein equations, which is this tensor h mu nu. This h has nothing to do with the Hubble function. It is a tensor which is called this way, h mu nu 1, okay? In fact, in general, you need two tensors of this type, but for conformal space-time, as the Friedmann-Lemaitre-Walker metric, you just need one. This is just the variation of r square, okay? So it is a higher order derivative term. But okay, I will not go into these technicalities, but I need to introduce this contribution here. The next point is that with the renormalized, with the vacuum energy, the expectation value of the vacuum energy, which it was defined in this way from the very beginning. If you take the 0,0 component, then you can project the density, raw vacuum density, at the scale m. So you see that the vacuum energy density is not just the raw lambda term in the action. It is that term plus, of course, the contribution from the 0-point energy, the normalized one, following the previous prescription where we subtracted the value at this scale m. And in this case, it is divided by a squared because I'm using the conformal metric, and I have to include this term here. So when I evaluate this expression in terms of this formula that I have given before, I get that the vacuum energy density is given by these terms here, which are constant, and these terms here, which, as I said, evolve with the expansion, okay? Now, the important thing here is the following. The important thing is that this evolution of the vacuum energy in the universe, in this framework, is completely smooth. You could say, well, why is it smooth? Because we have a quartic power of the masses here, and this could provide a large contribution. It is not so. It is not so because, you see, let us come back to flat space. If we are in flat space, then these two terms here, this and this, they are, you can kill them because h is 0. So you are left with only this expression. Now, if you compute this derivative, the derivative of raw vacuum, I mean this first line here, as a function of this scale, this derivative must be 0. Must be 0 in flat space because this vacuum term here comes from the bare term of the theory. So the bare term was just replaced by the normalized one plus counter terms, okay? But the bare term, it does not depend on the scale. Therefore, this expression does not depend on the scale, despite there is a dependence on rho lambda, and there is some explicit dependencies here. But this cannot depend on m. I have written m here because it will depend on m if I put all the other terms. But if I consider only the flat space case, this expression cannot depend on m. So it means that this partial derivative with respect to m is 0, respect to this normalization point is 0. And then it means that the corresponding derivative of rho lambda, this one here, which provides the beta function of this parameter, is related to these other terms. You perform the derivative, and what you get is that is given by this expression. You see that this expression is quartic in the mass term. It is also quartic in the normalization scale, but this is only the evolution of this parameter rho lambda this is not the evolution of the vacuum energy, because the vacuum energy does not evolve at all in flat space. However, if we repeat the same prescription for the whole term, which contains the dependence on h, and now I compute the derivative with respect to m, again, of the whole expression, of course, the first two terms cancel, because this is what we have said before. And then the only thing you have to do is to compute the derivative with respect to this m here, okay, and this m here. And what you get is this expression, which contains two pieces, one which is proportional to h squared, and another which is proportional to higher order terms, h dot square, h double dot times h, okay? Which we can, for the moment, I'm not saying that they is zero, but we can neglect for the present universe, because they are much smaller than the dominant term, this one here. And you can see that the evolution of the vacuum energy with the renormalization scale is no longer quartic. It is quadratic, m squared, h squared. Okay? So you don't have m to the fourth like here. What you have is just m squared times h squared. So if this mass, whatever it be, this mass, doesn't matter that it is the mass of the top or the W or whatever, or any heavy mass, this mass will be multiplied by the value of the Hubble function at present, for example. So this term h squared times m squared is a soft term, is not a hard term as it was the m to the fourth that we got before. That term just cancels in the normalization process. So the evolution of the vacuum energy defined in this way, following the prescription that I have given before, is an evolution which is perfectly smooth with the cosmological expansion. So there is no need of fine-tuning the structure of the vacuum energy in this framework. So this provides a new view of the cosmological constant problem, if you wish, okay? Well, I realize that my time is exhausting, but I want to show you what is, I mean, if we forget about the higher order terms, then let me show you what is the expression that, according to this running vacuum model, we get for the vacuum energy at the present time. So the expression is that the vacuum energy at any, well, that's the point that I wanted to show, that then once you have these formulas, of course, you have to give a value to your normalization point, as we do in any, I mean, in any quantum field theory of particle physics, as I mentioned in the beginning. In this case, my association of m is given by the value of the Hubble function. So if at any time of the cosmic expansion we associate the normalization scale to the value of the Hubble function, then the result is that the vacuum energy at any time, okay, is given by, for example, the value at present plus this term, which is quadratic in h. As I said before, it is a product of a mass squared times h squared. The only thing that I have done here is just to normalize this expression such that when h takes the current value, we get the current vacuum energy. Okay, there is nothing else. Apart from that, it is the same expression as before. I have also introduced the Planck mass explicitly, but it actually cancels. It cancels because this coefficient contains the Planck mass square here, but it is convenient to present the result in this way, because then this coefficient is dimensionless, okay, dimensionless. So basically, what we say is that the vacuum energy evolves with the expansion, and it evolves in a very smooth way. There are no quartic contribution of the fields here. And the only thing that we have is some coefficient, which in fact is not a coefficient, it is a function. But it evolves very smoothly because you see there is a lock here, and then there is another lock. This lock is suppressed by h when you move back, for example. Okay, so this expression is essentially constant, and therefore it can be approximated this by a coefficient, a constant coefficient, which is this lock here at present. This is a big lock, actually. And that's why this -1 can be neglected as compared to this lock here. So this is constant. And then there is this small coefficient, which depends on the ratio of the masses of the particles versus the Planck mass times, in this case, the non-minimal coupling. You see, the non-minimal coupling was not essential to introduce from the very beginning, because even if even if psi would be 0, you still would get a result, right? So it is not that epsilon is 0 when psi is 0. No, psi can get any value or even 0, and you still have this coefficient, which can be interpreted as the beta function coefficient of the running of the vacuum energy. Okay. And with this expression, one can do some cosmology. So rather than introducing, for example, introducing quintessence, some quintessence field or phantom field or whatever, in order to endow the vacuum energy with some dynamics, you endow the dynamics with this expression, which is computed from quantum field theory. Okay. And using the vacuum concept, which we have freed from weird contributions proportional to the quartic power of the masses, okay? So it is a perfectly reasonable expression in principle, without introducing extraneous fields in our framework. The evolution of the vacuum energy as compared to the other densities is of course small. You can also, now I am going fast, okay? You can solve these equations for inflation, taking explicitly this h to the 4th term. This has been done in previous papers, okay? The difference is that now these terms have been predicted, not just assumed. They have been predicted in this framework, okay? So these calculations, for example, they were performed on this model, and it was basically just based on semi-qualitative arguments, okay? Now these terms are predicted, so these calculations now adopt a different status. And in this framework, you have a vacuum energy very large in the past that decays, and then it decays into a radiation. So radiation was very small in the beginning, it increases, and then it decays up to the present. So this is how we describe inflation in this running vacuum model idea, okay? So it is also incorporated in this framework. And then one thing that I would like to mention, if you allow me, is the equation of a state of the vacuum, because this is surprising. We can compute the pressure of the vacuum. I will not go into details because, again, this is a complicated business, but it has many contributions. But if one takes the leading contribution at present, so you see the pressure of the vacuum is minus raw vacuum, as we would expect usually, plus corrections. Don't forget these plus corrections. And the first correction is given by this F2 term, which is proportional to h dot. So it is of order h square, right? So when you just take this correction and you compute the equation of a state of the vacuum, which is the ratio between the pressure and density, then it is, of course, -1 plus something. Okay, this something is what is given by this leading correction F2. And when you perform explicitly the calculation in terms of the redshift, you get -1 plus this function here. So now we have three regimes for this vacuum equation of a state. For example, suppose that we are at very large Z in the radiation epoch. Then this is the dominant term, 1 plus Z to the fourth. You see, there is another 1 plus Z to the fourth in the denominator. These two coefficients now cancel because these terms are dominating upon the others. And you just get minus 1 plus 4/3, which is 1/3. So the vacuum equation of a state behaves like radiation at very large Z. If you move down at the epoch of matter domination, then the dominant term is 1 plus Z cubed. This one is now negligible. So now you just take this one and this other one, which also goes like 1 plus Z to cube, and now you get minus 1 plus 1, 0. So, and in this region of which is matter-dominated epoch, the vacuum equation of a state behaves like matter, 0. Finally, at low redshift, the only term that matters is this one here and this one here, because now this is these ones here would be negligible, would be order nu square. Okay, so the only contribution is minus 1 plus this term divided by this term. So minus 1 plus nu effective and the ratio between omega m matter and omega vacuum and 1 plus Z cube. So you see that the vacuum at low energy now behaves like quintessence if this coefficient would be positive. Remember that this coefficient was computed before, so it is not something that we put by hand now. And if this coefficient is negative, it will behave like phantom. So the vacuum can behave like a phantom dark energy at low energies, low redshifts. And it can behave as quintessence, and it all depends on this coefficient. Let me add that this coefficient is, well, this is what you have here, okay? So the vacuum equation of a state, which was presented in this paper, you see it behaves like quintessence, for example, in this case, because we assume that nu is small but positive. And then when we increase the redshift, okay, so it behaves like dust, 0, and it behaves like 1/3 radiation. Here we have the two possibilities. This is what I have discussed before. And here, when I assume that nu effective is negative, then you see, oh, sorry. You see that there is a phantom behavior because it goes below minus 1, okay? This thing here is just an asymptote which appears because the density becomes 0 at some redshift. But this is no singularity at all. Pressure and density are perfectly finite. It is only that the ratio, when you compute the equation of a state, goes through this 0, okay? But before that and after that, it is perfectly well behaved. This is a style in these papers. When you consider this calculation both for scalars and for fermions, which we did in this paper quite recent, again with Christian, and here we also with the collaboration of Samira Cherakchi, then we obtained the contribution from an arbitrary number. I mean, the contribution to this beta function for the running of the vacuum, a contribution from an arbitrary number of scalars and arbitrary number of fermions. You see that fermions contribute with a minus sign. So this nu effective here can be positive or negative depending on whether you are dominated by a scalar or dominated by fermions. And in each case, I mean, you will have an equation of a state that at low energies will behave like quintessence, or it will behave as phantom. It will depend on the domination of these terms. Of course, we cannot say at this point which one dominates because there is a sum here. It will depend on the kind of fields that you consider, okay? But this is a generic result, okay? And it shows that the vacuum, in fact, behaves perfectly smooth, and it mimics it may supplant the role of quintessence or phantom dark energy. So there is no need, from my point of view, to reject the vacuum as a perfectly viable option for dark energy. Okay,
Joan, maybe
yes,
we could conclude
that's
in a
right.
little bit. Yeah,
That's
very
right.
good.
Thank you very much. The only thing, just 1 minute, if you allow, is that this has phenomenological implications. I don't have time in this talk, of course, to go into these details. But I can tell you that I mean, there are papers, of course, showing that using these kind of models, you can enhance the value of 8.0. Okay, so here you have the contours. Okay, and decrease the value of sigma 8. So it helps to smooth, to ease the tensions. I mean, I don't have time, of course, to comment on these tables, but in any case, they are in these papers here with my collaborators. Okay, I don't show this. You can just check it if you like. So my summarized conclusions is that dynamical dark energy, I mean, is a natural proposal for expanding universe. But the idea of vacuum, overrunning vacuum, okay, is sensible. It usually goes accompanied with the running of gravitational constant, a very smooth one, logarithmic, and with that small coefficient. Okay, and when you put all these models into test, to the test using usual cosmological data, okay, we get a quality fit, which is no less than the standard model, than the CDM, and sometimes even better, and can explain a lot of features, in particular alleviate the cosmological tensions. So these ideas may signal a connection between the large-scale structure of the universe and the quantum phenomena in the microcosmos, because we have used quantum field theory in order to try to describe the cosmological physics. So thank you very much, and sorry for the extra time.
No, thank you so much for an interesting and exhaustive talk. Very good. And I open the floor to questions and just unmute.
Hello. Thank you. Thank you very much for that talk. It was really dense and very exciting and informative. Like, I'm definitely going to check out your the reviews. Yeah, it's awesome. I love it. But I don't want to waste your time. But it's I would you help me understand like the intuition or what it means to have the vacuum energy expressed as a sum series in an expansion rate of
in the Hubble
space?
rate.
Yeah, just like what
Yeah.
does it mean? So, yeah.
The meaning is, I mean, in a few words, is very simple. I mean, what we have is the vacuum energy. I mean, as we conceive it, usually is in classical general relativity is usually connected with just the cosmological term, right? So just a constant term, and that's all. Okay. Of course, this has a problem in the sense that this is a term it has to be very small, or it is very small when we try to compute quantum corrections to that term. Okay, as I have shown before, the quantum correction, these blob diagrams, they are divergent, and usually they lead to large contributions. Okay. So after renormalization, so it means that when you put your general relativity, not just general relativity, you have here general relativity plus higher order derivatives terms, r square, r mu nu square. Okay, so you have this. Okay, not just the Einstein-Hilbert term. When you put
Yeah.
this and then you assume that matter is quantized. Please notice that we are not assuming that gravitation is quantized here. Here we don't have gravitons. Of course, we could try to quantize the gravitational field in order to see what is the impact on these considerations. But we didn't do that because it is already sufficiently,
Difficult.
Yes, yeah. So the point is that if you just consider classical gravity, but not just Einstein-Hilbert gravity, classical gravity with higher order terms, and then you quantize matter, the vacuum fluctuations of matter, just of matter, okay, not gravity, these vacuum fluctuations induce additional terms, which are just the powers of h that I have shown. So
it's just, oh, sorry, carry on.
So, so that's right. They are just quantum corrections, which
so
are
in the vacuum you'll have parts that like the expansion will also be negative sometimes, like so you'll have some of it expanding and some of it contracting, and so the vacuum energy is just it affects expansion. That's all. Like, is that, I don't know, am I understanding it correctly? Anyway, it's quite interesting.
Yeah, maybe we could go to Simone.
Hello.
Hello.
Thank you very much for this talk. It was indeed exciting to attend it. I was wondering how could we interpret then the contribution of matter itself or radiation itself if this running vacuum behaves as matter or behaves as radiation in the evolution. Like, would we have an effective equation of state, for example, or when you say that this running vacuum behaves like radiation, it's because we don't need the radiation. It's just, it was a bit complicated for me to understand how can we handle with these other components, and also to the content itself of the universe, no? Because in lambda CDM, for example, we have like 75% of dark energy, and in this case, would we need other components, or we are saying that running of the vacuum is enough to explain everything? Because that's what, well, you can correct me. I'm just trying to understand.
Yeah, sure. I mean, this is a bit surprising in the sense that we are used that the vacuum is the equation of a state of the vacuum is just a rigid constant -1, okay, and in fact this is the equation of a state of the vacuum, for example, of this vacuum that I have presented here in the inflationary universe. I mean, when you have inflation, the equation of a state there is actually -1, as one can show, and it eventually, I mean, in the future, for when the universe starts to, well, it already started, but when the de Sitter epoch will again dominate, again the equation of a state will be again -1. But for the present time, what we get is this ambiguous behavior, in the sense that when we are at low redshift, okay, which is actually you say redshifts of order of the supernova redshifts, okay, so I mean redshift of order 1, let's say, okay, or even less, okay. So when we are in this regime, then the vacuum behaves, when you consider those quantum effects, behaves like -1 plus epsilon, so to speak. Okay, this epsilon can be positive or negative, as I said, depending on on which kind of spin will dominate in the contribution to that coefficient nu. So it behaves like quintessence or phantom dark energy at low redshifts. Then when we move to higher redshifts, then the vacuum does not behave as vacuum. I mean, at least this vacuum that we have computed here, it behaves like matter and radiation, and therefore, I mean, in any case, the vacuum is subdominant even if the equation of a state is -1 when we are at very large redshifts. The only difference here is that its equation of a state will not be -1 in this in that period of subdominance, okay, which we cannot you cannot easily track just because it is subdominant. But its equation of a state will be 0 or 1/3, okay? And so I'm at the moment I would say that the only access that we have to that equation of a state of this vacuum is at low redshifts, in the sense that if we find at some point that that dark energy is indeed dynamical, so suppose that at some point the measurements tell us in a very convincing way that the vacuum is evolving with time, okay? So of course people, I mean quintessentialists, so to speak, will say, okay, this is proof of quintessence. Or if it turns out to be a phantom, okay, it is proof that there is a phantom field there. Well, I mean, one could also say that perhaps it's neither quintessence nor a phantom, but it is just vacuum under quantum effects.
Okay, so maybe it's the fact that it behaves like dust or behaves like radiation means that it does not provoke other effects beyond the ones we know, right?
Yeah.
But
okay. That's right. I mean, especially in that region, which is subdominant. Yeah.
Where we have observations confirming that it's that way, so it does not make other strange things. Okay, so very good. Thank you.
You're welcome.
Perfect. And I think we have a question by Giuseppe.
Yes, can you hear me?
Yeah.
Yeah.
First of all, thanks a lot for the very interesting and clear presentation. I really appreciated it. And mine is just a curiosity, really. I was wondering if the coefficient of the minimal coupling of scalar fields to matter were to be 1/6, then all of your calculations would simplify significantly, but
exactly.
also the dependence of the vacuum energy density upon the expansion of the universe upon cosmology would disappear.
That's
somehow ruining the work. And so just what would be the interpretation of such possibility?
Yeah, very good question. Well, of course, this is true, except that that this only affect to the scalar fields, because the fermions were not affected by that coefficient, right? So even if psi would be exactly equal to 1/6, all these contributions from scalar fields would disappear. Then we would be left with only fermions, and in that case, the vacuum energy would surely behave like phantom.
Mm-hmm.
It would behave like phantom, because there could not be the possibility that cancellation between scalars and fermions. So okay, so we would have a phantom-like behavior of the dark energy. But apart from that, which is of course one possibility, I mean, this factor of psi or -1/6, I wanted to keep it there. It actually complicates a little bit the calculation, but I wanted to keep it there just because I wanted to see exactly what you have seen. I wanted to see that all my results would go to 0 when psi is equal to 1/6. And this is, of course, a way to cross-check the calculation. I mean, is a way to make sure that you get what you wanted when the theory is conformal, okay?
Okay.
But on the other hand, it is difficult to believe that the non-minimal coupling of all the fields all the scalar fields are equal to 1/6. Remember that there is a sum over contributions. So I can understand that, for example, this occurs for some particular field, but there is no reason why all fields should be conformal. But even if they are, for whatever reason, we are still left with the contribution from fermions, okay? Which would go.
And why shouldn't you include a psi-like coefficient also for fermions? Why wasn't that?
Oh well, but because there is no minimal coupling of
Okay.
to fermions, okay? The no minimal coupling, I mean, the interaction, I mean, I can show if you wish. It is here. Yeah, you see. This is the general form of the new coefficient, okay? So in the case of even here, you have the action. So the action for scalars takes this form, okay? The action for fermions takes this form here. And in this form, you don't get this psi. You cannot get this coupling because actually there is already a non-minimal coupling here, which is hidden with the covariant derivatives, okay? And there is a non-trivial coupling between the fermions and gravity in these covariant derivatives. But in the scalar field is more explicit through this arbitrary coefficient that you can put here. So so yes, and
Okay, I see.
you cannot kill the contribution from fermions by making some special choice of a parameter.
Perfect. Thanks a lot.
Okay.
Then we can go to Carla.
Yes. Hello.
Hello.
Thank you, Joan, for your very nice, interesting seminar. So I had a question. You consider the 0-point function, the 0-point energy, and you normalize it. And after this proper quantum treatment, you obtain that the cosmological constant problem is alleviated somehow, right? So you pass from this mass to the fourth to this mass to the mass squared. If understood correctly, you neglected the fact that some field can acquire a vacuum expectation value. Is that correct?
That I neglect what? Sorry.
Some vacuum expectation value that some scalar field can assume, can acquire.
Yeah. I did not consider the contribution for this calculation. We did not consider the contribution from an effective potential.
Exactly. So
Yeah, of course. I mean, this is not the end of the story. One should include B phi, and then of course this B phi would also include quantum corrections. Okay. My conjecture, but at this point is just a conjecture, is that when we would perform the subtraction of the energy momentum tensor at that arbitrary scale m, in which is necessary in order to kill the divergences of the energy momentum tensor, then the same kind of pattern would emerge, okay? And that we would not have these quartic contributions, okay? That would lead us too long to discuss this. So I will just say that my conjecture is that that this situation would be eventually recovered. But in any case, you are right. I mean, we need to deal with this next step. But if this one was cumbersome, the next one it is even more cumbersome, I would say. But maybe at some point, with the help of some student, we can do something. Yeah.
okay, thank you very much. Bye.
You're welcome. Bye.
Francesco?
Hi, do you hear me?
Yeah,
Yeah.
sure.
Okay, thank you again for the presentation. It was very nice. So I had like a bit technical question. Can you re-explain how you discarded the m to the fourth terms after renormalization?
Yeah. Yeah, I can do it. You can.
Okay, thank you.
No, yes.
I don't know if it's too long, but
Well, it can be long, but in any case, if you go to the papers, you will see all details there. But of course, you ask a question, I have to give an answer.
Thank you.
Yeah, sure. So this argument can be presented in different ways. I tried to make it as simple as possible for this presentation. If you go to our papers, specifically a paper of 2022, January, it's a rather lengthy paper, you will see the argument in other grounds, not these ones that I have used here. It's more detailed there. But in my opinion, this explanation is perfectly equivalent to the other one. So the point is the following. So we have this expression, raw vacuum. This raw vacuum contains this constant term plus the dynamical terms, which depend on the expansion, right? So when you look at this, you may be worried by the fact that these quartic powers here and here and here would add a large contribution to the vacuum energy, okay? But this is not so, because there is a subtle interplay between this term here and this term here. This rho lambda, remember, that is the cosmological term in the action, okay? Rho lambda, I mean, is the term that you would insert in the Einstein-Hilbert action, okay?
Yeah. Okay.
And which usually people believes that this is the vacuum energy, and that's all. No, it's not. The vacuum energy is not just this. As you see, the vacuum energy is here, and it is a sum of many other things. It is the sum of this term that you have already there since the time of Hilbert and Einstein, okay? And then you have, in the presence of quantum field theory, you have other contributions which add up to this term, and the sum of them all provides your vacuum energy, your final renormalized vacuum energy. Now the question is how these two terms relate one another. Because you see, these other two at the end, these are very smooth terms because they are proportional already to h square, m square, and this one is just the log of m square, so it's completely innocent term. It will not harm us at all. This one will not harm us at all because it is also this product of mass square and h square. So the only problem is focus on these terms here. But these terms do not do anything at all. It is just, they are fake terms, so to speak. Why? So let me repeat the argument. Suppose that we are in flat space, Minkowski space. If we are in flat space, the two terms on the second row would not be there because h is 0, right? A is constant, so h is 0. So you are left with only these two terms precisely, okay? Now, what was the argument that we did at the beginning when we considered the flat space, Minkowski flat space time? We started with rho lambda in the vacuum in the Einstein-Hilbert action, but this rho lambda was rho lambda bare. It was a bare parameter. So we have to use here the standard arguments in renormalization theory. We start from bare parameters, and then we have to go from the bare parameters to the renormalized ones. In order to go from the bare parameter to the normalized ones, you have to split each bare parameter into a renormalized parameter plus a counter term, okay?
Okay.
And then when you do this, the counter terms cancel the divergences, and then you are left with only the renormalized terms, which are finite. However, they are now dependent on a renormalization scale. In the beginning, the bare parameters are not dependent on any scale at all. But once you renormalize the theory, whatever it be the normalization scheme that you use, for example, if you would use minimal subtraction, then you would use this famous mu parameter, okay? But this mu parameter is different from the m parameter that I'm using here. But in any case, you need a renormalization scale. Okay, so once you have renormalized the theory, you are left with a dependence of all parameters on this scale. However, in the beginning, what you call the vacuum energy in flat space was a bare parameter. So it doesn't have any dependence on m on the renormalization scale. Once you perform the split of each parameter into a renormalized one plus a counter term, then you are left only with the normalized parameters, because as I said, the counter terms kill the divergences, okay? But this operation does not change the fact that the initial quantity was a bare parameter, and therefore it does not depend on m. So even if there is an m dependence of this parameter and an m dependence explicit here and here, the sum of m dependences of these two terms must cancel in flat space, and then it will be always so. So you go now here and you say, what is the derivative of this vacuum energy with respect to m? 0, because we said that this was a bare parameter. If it is 0, then it means the derivative of this is equal to minus the derivative of this other term. This is what I am doing here. So then you get that the derivative of this term gives exactly this term here, which is a quartic, as you see, is depending on the quartic power of the mass, okay? So this becomes established, and then in the next step, when you consider the full expression, I mean, with these terms, which depend on h square and h to the 4th, now you perform again the derivative with respect to m here and here, but the previous derivative still gives 0, okay? So these terms do not participate in the computation of the beta function of the vacuum energy. And so the only thing that you are left is with the derivative of the dynamical terms, the ones which depend on h, the derivative with respect to m. And as you can see, when you perform the derivative with respect to m, you get, for example, here 2 times m h squared. Since you multiply the result, as it is usually done when you compute the beta function for times m, then of course you get m squared h squared, okay, and you also get the mass term squared times h squared. So the final the upshot of all this is that the beta function of the vacuum energy evolves in a very smooth way, because it is proportional to the value of the Hubble rate squared. At present, of course, this is very small, and no matter how big is this mass, the product of the mass squared times h squared is just a small correction to the classical Einstein equation. Okay.
Okay, thank you so much. So it's the beta function that does not depend on m to the 4th, and so
That's right.
then you compute the evolution of raw vacuum
Exactly. So since it does not depend on m to the 4th, it doesn't matter if you have a correction of which is of order of the top core mass, which is big, for example, very big. The evolution of vacuum energy will be this m squared times h squared. Therefore, it will be small. But despite it is small, namely, despite that coefficient nu effective that I mentioned is small, when you introduce this small effect into the fitting of the cosmological data, this helps in order to improve the fit. If you go to our phenomenological papers, you will see that we never get a quality fit, which is worse than the standard model. On the contrary, I mean, we can even get a better fit, and we can even get a help in order to solve the cosmological tensions, 8-0 and sigma 8. Okay, I didn't have time to explain this, but I have shown some plots, and you can go to the papers. So these small effects, of course, the decay cannot be big. The standard model is essentially correct, essentially, but essentially it doesn't mean that it is perfectly correct. It is obvious that in the standard model of cosmology, lambda is nothing. I mean, it's just a parameter. We have fitted this parameter. Unless you put some structure, some understanding, some quantum field theory or something behind, you are not understanding the standard model. And when you try to do this, you get these kind of things. And these kind of things, as you may see, help in understanding the cosmological constant problem and other problems of cosmology.
Thank you so much.
We have another question by Bonang. Maybe we could close on this question. Bonang, maybe unmute.
Hello, can you hear me?
Yeah.
Okay, thanks for the wonderful presentation. The question that I have, maybe I might have missed it, is how does the model solve if the model does it solve the Hubble tension and the sigma 8 problem? And the other one is due to the corrections that were made in the equation of state. Are they due to those quantum effects correction? Are they the one that gives the alleviations of those tensions, and the one for the cosmological constant problem that we have currently?
Thank you. I think I did not follow at least the last part of the question, but basically you asked how the model solves. Well, I'm not trying to say that it solves the cosmological tension. What I would say is that it alleviates, it helps to smooth these tensions. I mean, I do not pretend that it solves perfectly the tensions at all. I mean, let me show, for example, this phenomenological analysis that we did quite recently, as you can see here, with my collaborators and former students. So for example, in one of the situations that we have studied, the fitting analysis provided these results. For example, 8-0, you see it is 71.7, so it's quite close to the value of 73, essentially 73.04, something like that, by choose, okay? And even the value of the absolute magnitude, which for this collaboration shows is minus 1920 something. So here it is minus 1931. So the value of sigma 8 is also smaller than in the standard model. And here you can see that the overall quality of the fit measured by the deviation information criteria. So this is the difference between the standard model value of DIAC and, in this case, a running vacuum model value. So it is plus 13.78. So this means that the fit provided by the model is much better in this case, not in all the cases, but in this case is much better than in the standard model. So So this means that that we are helping here. I mean, we are not getting exactly what we want, 73, but this is around 1 sigma away only, not 5 sigma. Okay, and also for the value of the absolute magnitude, for example, which you will have to control at the same time with the value of 80, is also just around 1 sigma as compared to the concordance model. Okay, and this is one of the realizations of the running vacuum model, which we call type 2. There are other realizations which do not work so well, but do not work so they don't work so bad after all. They're in all cases reasonable. For comparison, you see, for example, here the XCDM parameterization, or if you want the WCDM parameterization, the same, which is the same thing. Okay, if you compare the performance of these kind of models to a performance of a generic parameterization of dark energy like XCDM, you can see that the value of H0 is not that big as in our case, and the overall fit quality, you see it is even negative as compared to this plus 13.78. So it is clear that not every dynamical dark energy model or parameterization will get the same fit quality as compared to, for example, this realization. Okay, and in another realization, which we call type 1, for example, we do something different. You see, now we cannot address the Hubble tension because it is smaller. Okay, the value of H0, but we still get a very large fit quality, plus 10, and this is because we basically solve completely the sigma 8 tension. It adjusts this tension very well, and the reason is because here we assume we just do some game which has been recently played by many people. We assume, for example, that there is a change of behavior of the vacuum at redshift 1. So suppose that the vacuum is constant. I mean that there is a true cosmological constant from the CMB epoch, I mean from the release of the CMB epoch, the decoupling epoch, up to Z equal 1. But then at Z equal 1, suddenly the vacuum gets activated and becomes dynamical. And its dynamics is precisely the one predicted by the running vacuum model. Under this assumption, then you can solve, or at least highly alleviate the sigma 8 tension, although unfortunately it doesn't have an impact on the H0 tension. However, in the previous realization of the model, here we are not assuming anything like that. I mean, the vacuum is vacuumal. I mean, is not. It doesn't have this threshold at Z equal 1. It is normal 1. But here we take into account the fact that the gravitational coupling can be running, as you have seen. These kind of models predict that the gravitational coupling is running. So in this realization is when we get this scenario. Okay, so we do not have just one particular definite and unique scenario. There are different scenarios around the running vacuum model idea, but in all cases, the framework emerges from this kind of calculation based on quantum field theory.
Thank you.
Thanks a lot, please. I appreciate it.
You're welcome.
So thank you again for a very nice and exhaustive presentation and Q&A session. Let's thank the speaker.